Welcome back. This is part 2, and this time we're going to look at the periodic trends or patterns in it, and it follows directly onto some of the things that I forgot to mention in the previous video, namely the terminology we use to describe certain features of the periodic table. And this numbering system is old school, so please ignore this number. So the first feature we're going to look at is columns. These columns on the periodic table are called groups, and a group is a selection of elements with similar chemical properties. So for group 1 elements, they all should have very similar chemical properties to each other, as we mentioned in the previous video. Those are the alkali metals. And the group 2 elements, they are the alkaline earth metals. And group 17 is the halogens, and group 18 is the noble gases, and the ones in between, not all of them actually have a real nice name, so I've just highlighted to you the main ones. Groups. Please be extra careful in your use of the word group, because that obviously has an everyday meaning in our vocabulary on an everyday basis. However, if you have to talk in terms of chemistry about periodic tables, you may want to choose your words carefully, because the word group has a very specific meaning. Okay, it specifically refers to these vertical arrangements of elements that have the similar chemical properties. So you may want to choose a different word if you were trying to describe a collection of stuff. Okay, be extra careful. The groups are numbered, so we've got group 1 all the way up to group 18, and they are one number for each respective group. Sometimes these are written in Roman numerals, so just be aware of that. And sometimes they may not even go up to number 18. Sometimes they only go up to number 8. And that's because they don't necessarily have a numbering system to take into account of the transition metal block, or the D block elements, which have 10 groups spanning across them. So if you take 10 away from 18, what you're left off with is 8 groups. So that's why sometimes you'll find periodic tables which have only 8 groups written above them. Next thing we're going to look into. Ionic charge is related to the group number for commonly used groups. So this won't apply really nicely for all the elements, but for the ones that we use a lot in junior science and sometimes senior chemistry, they have a really nice rule of thumb. So what I'm talking about here, ionic charge, that is the charge that an atom would become after it has exchanged electrons. So when a element, so let's say elemental lithium, reacts with another non-metal, they will have an exchange of electrons such that they can satisfy their valence electron shells, which we know from the atomic anatomy of the atom series. So they will do an exchange of electrons if there's a metal reacting with a non-metal to make a compound. And in that process, usually each of those species, the metal will become a positive charge, the non-metal will become a negatively charged atom. And we call these charged atoms ions. So the metals become positive ions, and they're all called cations. But I'm going off topic. So the alkali metals, they will become +1 charged, and the alkaline earth metals will become +2 charged. And it's really quite handy if you just look at the group number. And you can even write this. You can draw a little cartoon of this rough shape and draw the little plus and minus signs above them to help you remember. So we can just go +1, +2, +3. Why they become those charges, I'll have to explain in another video specifically about ions, but for now you'll just have to take my word for it. For the other side, where the non-metals are generally found, we have to count from the other way. So group 18 elements, those are the noble gases, and they're named noble gases because the nobility don't necessarily interact with the commoners or the other people. So they don't interact with anybody, not even with themselves, so they have no reason to actually exchange any of their electrons, because they happen to have a full set of valence electrons anyway. So they will have no charge, they never become an ion. the group 17 elements, the halogens, they are so close to filling their outside shell, they will steal whatever they can to fill that last remaining place and become a negatively 1 charged ion. The group next after them, they've got 2 electrons to go, so they become negatively 2 charged, and so group 15 elements also become negatively 3 charged. Group 14 elements, you can almost look at it, it's right halfway, it's right in the middle of the road. We've got the elements to this side, they become positively charged because they give up their electrons. And on this side, you've got elements that are very close to filling their shells, so they steal them and become negatively charged. What happens to the elements right here in the middle? Well, it's not so easy. When you're halfway across the road, they don't play this game of exchanging electrons, at least for the ones that we mostly care about, like carbon and silicon. Silicon sometimes it's a metalloid, so it can behave a bit like a metal and a non-metal. But for carbon especially, it doesn't play the game of exchanging electrons. It plays a different game, which we call covalent bonding, where it actually chooses to share electrons rather than to give them up or steal them. So it doesn't actually it doesn't form an ion, and that's mainly applying to carbon. The ones below that becomes more and more metallic, so you have to kind of, these are very rough, very loose rules of thumb, but you won't deal very much with the elements in here on an everyday basis in junior chemistry. So, moving on. Next feature we're talking about is the rows are called periods. As we mentioned in the previous video, it's called a periodic table because the elements, or the character of these elements, are repeating every so often in terms of atomic number. And every time it repeats, it's a new row. And so we call each row a period. So we go across this way from hydrogen to helium, then the cycle repeats where we get another element that has 1 electron in its outside shell, and then it makes a new cycle till we get another one that has a full set of electrons, just like helium did, and so we begin the next cycle, and that's why we call them periods. And they have their numbers usually written on the left-hand side here of the common periodic table. Simple. Okay, another thing to mention is that the table itself is broken up into larger chunks. So the red bits I've colored in here, those are the non-metals. I think it's self-explanatory. Those would be things like carbon, nitrogen, oxygen, fluorine, and all the noble gases. Those don't behave like metals. The ones that are, a vast majority of the elements do behave like metals. So you'll find copper, iron, aluminium, cobalt, magnesium, all these metals that you see on an everyday basis. They are located in the large portion of the periodic table. This boundary here of yellow squares that I've shaded in, the boundary between the metals and the non-metals, these are called metalloids, and that is because they have similar characteristics to both worlds. They kind of got 1 foot on either side of this boundary, so they actually have a similar set of characteristics to both. Very strange indeed. So those are metalloids. I haven't shaded them properly, I just put a rough staircase in here, but you will find that in this common periodic tables they'll have an extra thick line outlining the separation between these two worlds and which one's the metalloids. And I believe that's all I've got in my list here. Please make sure that when you are talking about periodic tables, try to avoid using things like rows and columns, because those two things of a periodic table have specific terms, that is the groups and periods. I don't remember if I got them the right way around in terms of what I just said. So the rows are periods, the columns are groups. Because there's specific terms for those two things, try to use them instead of the everyday vocabulary. The more you can use the chemistry terminology, the smarter you sound, and it often takes less words to say because you have used a very precise term. So there's advantages to that. And that's all for this video. Oh, something I forgot to mention. So the Ionic Charges up here, some of you may have noticed that I haven't written any for here. That's because this transition metal block, and for the lanthanides and actinides, or lanthanoids or actinoids as I think they're more commonly called now, they don't play ball really nicely in terms of nicely defined rules. Transition metals, they have so many different possible ionic states, or oxidation states, you could almost call them. That's the +1, +2, +3 charges. Sometimes the same element can have many different possible charges, and that makes them unpredictable. So we don't have a hard and fast rule for these elements here. So we often just have, like, either we remember them, for example, iron, it can have +2 or +3 charge. Copper can have a +1 or +2 charge. And how do I know this? I've just memorized it because we use them so often. But just keep that in mind, that transition metals, there's no hard and fast rule for what their charge will become, what their charge will be once they've reacted and exchanged electrons. Same can be said for the elements roughly in this quadrant here. They also have a sort of a unpredictable ionic charge. You have to kind of look it up or work yourself backwards using the power of deduction, which I discuss, I believe, in a video that I made last year or the year before, where I talk about how to write ionic formulas. I believe in that subject area of ionic formulas, if you go to those videos, you search on the channel using the search tool, I actually tell you about how you can work backwards to figure out what charge some of these metals are if it has already been pieced together as an ionic formula. That's it, guys. That's the end of this video.